and what? It's too loud. Okay, hi everybody. Welcome to this lab. And this lab is all about waves. We have a lot of people who are not here. More than half the class is not here right now. So I hope they did not forget that they're doing their lab in this class and they should focus on it. Anyway, did anyone see the instructions for the lab?
Not yet.
Oh no, okay. Basically, there is like I was going to say a million videos, but probably I would have exaggerated if I said that. There are a lot of videos on that one. Oh, there is. Did we use a different link for Canvas? Let me check the messages because there is a. Ethan is thinking that, okay, I have a message in here. Hopefully it's not from one of you guys.
I got here from the same link we used last time, but I was worried that this wasn't the right link this time around. So maybe people were thinking that you were going to post another one.
No, I usually don't change it. Let me send a quick message to tell them the class started, and basically the link is here so that they know that they're. So this is Physics 100. And let me stop the recording because I don't want this to be part of the year. Although we have more people now joining. Okay. Okay, where is my announcements? And the announcements are last one, Zoom session. Okay, let me copy the whole thing. Announcements. I think the problem is from my end as far as this internet in here because I was trying to do something that disconnected everybody. Okay, I have more and more people coming. I think the link is working, so hopefully everybody will be here on time because we have a lot to discuss today. It's basically, Melissa, for some reason your picture looks like you're looking at me, but it's a picture. It looks like it's a live one, so it's confusing. Anyway, so let's get into the lab. So this lab is all about the waves. Hopefully you guys had a chance to look at it. Before I do that, did you guys do waves already in your lecture or not yet? Oh.
Waves? Is that what you said?
Yeah, waves. Like, did you do oscillations at least?
I don't think we've gone over that yet.
How about the oscillations? No?
I don't think
Okay.
so.
Okay, so let me, in a nutshell, cover two things, okay, in here. That's basically to tell you what the wave is and the main properties of the wave are, and what they are, and then also how is that relevant for our lab. So I'm going to share with you, let me get my notes in here. So basically, an oscillation is like, for example, when you take a, what happened? For example, when you have a mass attached to a spring, so basically here a spring, and you attach to it a mass, and you pull the mass out of its equilibrium and you let go of it, it's going to oscillate. So basically it's going back and forth, back and forth, back and forth. And that oscillation is, let's say, for example, the spring is attached to a wall or something. Another kind of oscillation, for example, is the pendulum. Like, for example, a clock. So basically, attach a string and attach to it a mass, and you pull the mass out of the equilibrium, and you let go of it. It's going to go back and forth, basically, in an oscillation. This displacement, in this case, an angle, the maximum it's going to go to is called an amplitude. How far out of the equilibrium it's going to go. And it's going to go both ways, the same distance. So if this was theta naught, the other one is theta naught. So basically, it's going to go back and forth. That's really the amplitude of oscillations. Same thing in here. So if you have a mass attached to a spring, and it's going to go as far as a certain distance d, then it's going to oscillate between positive d and negative d out of the equilibrium. So at some point it's positive d, and some point it's negative d. In other words, the spring will stretch a certain amount, and then relaxes back to its equilibrium position, and then it compresses back to its the same value. So it's going to be decompressed. I'm sorry, elongated, then decompressed, and then compressed again. So basically, that's the oscillations of a mass around the spring. So we call this one oscillation, and it's characterized by the time it takes, because they can go very slow back and forth. So that's called the period. To leave the oscillation from one point, go all the way and come back to it, the time it takes to do it is a period, and it's a time in seconds. Also, so that's one characteristic of oscillation, and we need that for the wave. So one of the properties of an oscillation is a period, and period is a time it takes, and it's a time, so it's in seconds. It takes to do a full oscillation. You leave it, you go all the way, and you come back, and you're measuring the time. So that's a period. For example, the clock that ticks the second, its period is 1 second. So basically, if I have a clock in here, every second it goes back and forth. So that is its period. I have, if I'm going to adjust it and adjust the tension on all of the springs and everything else to make sure it's properly working, that means every time it's going back and forth, it's going to go 1 second. Or the little one, the one for the second, goes around once, that's going to be a second. So that's the time it takes. Obviously, the big or the thick one, the short one, it takes about what, an hour to go around? So that's its time, that it goes there. That's one thing. Then, if it's going too fast, for example, in 1 second it does 10 times, it goes back and forth. In other words, its period is 1/10 of a second. That number, how long does it go back and forth in 1 second, is called the frequency. So that's another thing that we need for this one. So frequency. Frequency mathematically is equal to 1 over period. So this one is in seconds. And the frequency, and you heard this word a lot, actually, a lot. The frequency is actually measured in 1 over seconds, because the time is in seconds, the period is in seconds. So this must be in 1 over seconds. But in honor of Mr. Hertz, who did a lot of work in basically telecommunications early on, so they call it actually this one in honor of him as Hertz, HZ, for the unit for the frequency. So those are two characteristics that we need from the oscillations. A third characteristic that we will need from the oscillations is called the amplitude. And the amplitude measures the intensity of the oscillation. So the amplitude is like that distance, for example, in the mass spring system. How far would it go? And then come back to equilibrium. It's going to be the same number when you go to the other side. So that's the amplitude. Or it can be measured in angles, for example, for the pendulum. How much is going to open up, and then how much is going to open on the other side. So that's basically, it can be the amplitude, the unit for it is whatever you're trying to study. It could be in centimeters, meters, could be in amplitude, for example, for the case of angles, it could be whatever your system you're trying to study. So that's basically what that is. Now, the big characteristic of what an oscillation is, it's localized. it happened in a specific point. So for example, the clock, when it ticks in its place. It's never going to leave the wall and go to somewhere else. It's going to stay in its place. So the characteristic of what an oscillation is, it's localized. Versus a wave. A wave, it's a disturbance that doesn't stick in its place. It's going to move from point to point to point to point. So it's similar to an oscillation, except that it's non-localized. It travels. So waves travel. If I take, for example, a string, not spring, string, a rope, and stretch it from both ends, and then on this end, no, I didn't do the attendance yet. I usually do it somewhere in the middle when I take a picture of everybody who's here. I mean, a snapshot of the session. So if I come to this end, basically, and do the following, create a disturbance. So basically, I'm here on this end. From this end, it's fixed. It's nailed to the wall. So from here, we're going to move it up and down, up and down. So what we notice is that this disturbance will travel through the string and will go all the way and until it hits to the other side. So this disturbance now became a wave. So it's in here disturbance, yes, but now it's a wave traveling in this direction. It's traveling to the right on my screen. I don't know how you look at it on your screen, but it's going this way. It's going from my left side to the right side. We call this one a right wave. Versus if I take a disturbance and send it in the opposite direction, or at least here, in this scheme in here, technically, usually when it hits the wall, the wave bounces off of the wall and comes back. So this wave now is traveling in the opposite direction, and this one is actually a left wave. So that's some of the characteristics of the waves that we need. Now, a wave, in addition to the three properties that I mentioned above, namely the period and the frequency, and also the amplitude, it has all of these three, plus it has something else, which is a wavelength. So it has a wavelength, and a wavelength basically is how much distance, that is in meters, between consecutive, for example, peaks in here, okay? Or consecutive lows in here, or troughs, okay? So that's a distance, and it usually uses the symbol lambda for it, the Greek letter lambda, and it's measured in meters or centimeters or something of units of length. So this is also fixed. So that's the distance, basically similar to the period where it repeats in time. This one repeats in space because remember it travels. I'm talking about a harmonic wave. This is called a harmonic wave because it looks like it's a sine wave. Now, another characteristic for the wave now, in addition to the fourth one, which is this one, is the so-called V, the speed of the wave. Okay, this is the speed of the wave. Some waves travel faster than other waves. For example, sound travels at 343 meters per second. Sound is a wave because it's produced, for example, from a source, and it travels in space and hits a receiver, and the receiver will pick up that sound. And sound, of course, comes with different frequencies. There are low pitches, basically sound that is very low, and there is high pitch, basically a sound that is very, very sharp, like, for example, sirens and things like that, that can go very high in the tone. So that's the tone. That's basically what we mean by the frequency. It's the tone. The ear, the human ear, is basically conditioned to hear only certain frequencies below which it cannot hear, above which it cannot hear. But there is a range for our ear that is sensitive to the sound. Sound is a wave. And also light is also a wave. So light is an electric field and a magnetic field, and they're traveling also. And it travels with the speed of light, which is 300,000 kilometers per second. So V is the speed of light, the speed of the wave, And it depends. Some materials are faster than others. As a matter of fact, sound, for example, in the air travels with 343 meters per second in a normal temperature. But if you put it, for example, underwater, it could travel for about 1,500 meters per second. So it's extremely faster in water than it is in air. For example, also in solids, for example, on the train tracks, you can hear the train on the tracks before you actually hear it coming from in the air. So sound travels with different velocities. So velocity is actually a characteristic that is important for the wave. So there are 5 characteristics: the period, the frequency, which are related, and then there is the third one, which is the amplitude, and it's characteristic for all of them. Amplitude for sound is called intense. There are some intense sounds, very loud sounds, and there are some sounds that are not so loud, very, very like the whisper. And the human ear also is conditioned to hear any range from the whisper basically all the way to super loud sound that can basically start to hurt the ear, basically called the threshold of pain. So at that point, after that, the ear might rupture, and basically the person becomes deaf. So basically, the intensity is another property of the wave. For light, the intensity of how bright the light is, basically. Sometimes some light sources are very dim, and some light sources are super bright. Okay, so that's really although the brightness has a relation to do with the power, and the power is actually related to the intensity in this case. Related to the strength of the electric field and the strength of the magnetic field inside light. So these are the 3 characteristics that are common with the oscillations. In addition to that, we have a wavelength. Now, the wavelength is measured in the units of distance versus time, which is measured in units of seconds. And the last property is the speed with which it's traveling from point to point. Now, waves have different behaviors. Waves can interfere with one another. One wave can come and work with another wave, and they can add up actually, or destroy one another. And all of these things will be examined today. So basically, you have, this is a right disturbance, right traveling disturbance. And if I bring another disturbance in here that is traveling left, and both of them are traveling in the same medium, for example, this is a cord, for example, a string, or whatever you want to think of it. So when they meet, they're going to go higher and higher. So this kind of interaction is called constructive interference, because once they meet, they're going to have a very high intensity. Then, because they are traveling, and probably they're traveling with the same speed in this case, because they're in the same and they're the same tension. So once they leave, they're going to leave as if they have never met. So this one, the one that was traveling to the left will continue to the left, and the one that was traveling to the right will travel to the right. But at some point, they will add up together. Now, if the amplitude was this way, but if the amplitude was in opposite direction, basically, let me draw another 2. So if this was like this, and this one was like this one, I'm sorry, and this was traveling that way, and the other one traveling this way. So once they meet, the amplitude will be a little, because it's actually an algebraic sum. So this is when they meet, probably, okay? And then at the end, when they merge exactly to the same way that they came in. So the one traveling to the left will continue to the left, and the one traveling to the right will continue to the right. So this kind of interference, the second one is destructive interference. The first one is constructive interference. So these are some of the properties that basically we'll be looking at today. Now, there is a very important property in waves that doesn't exist in oscillations. A wave can be characterized by a disturbance like this that is perpendicular to the direction of travel. So this is where it's going, but the disturbance is going up and down. So this kind of wave is called the transverse wave. Transverse means that it's perpendicular. The direction of travel and the direction of the disturbance, they're perpendicular to one another. They make a 90-degree angle between one another. That is the example, for example, for light, or wave is on a string. they are perpendicular to the direction of travel. However, there is another kind of disturbance, where, for example, sound, that the travel is in this direction, but it's going in this direction. So the wave is tracked. Basically, there are places where it's compressing, like slinky. I don't know if you've seen that or not. Basically, creates a disturbance in it, and that disturbance will travel all the way through in it. But the disturbance is in the same direction as the direction of travel. So this is a disturbance. In the case of sound, basically, there is a compression. The air is compressed, and then followed by a rarefication. The air is basically relaxed. But that is coming and going until it hits the ear. So the first, the rarefication will yank the ear out of its place, and then the compression will push it back, basically, and that's how the ear basically detects how loud the sound and how less loud it is basically by how much it moves back and forth. I mean, the eardrum, that is. And depending on how much it goes back and forth, that is the frequency, what we understand as being high pitch or low pitch, basically, as far as sound is. The intensity for light, again, is, like I said, can be expressed in terms of the brightness, but again, that's the square of the intensity, not the intensity itself. And also the color. Different colors are different frequencies, actually, different values. So these are some of the characteristics of waves. Now, one of the relationships that we're going to need in here is the relationship between the speed of the wave, the wavelength of the wave, and the period. So if somebody tells you the wavelength of this wave is, I don't know, 300 meters, and its period is 2 seconds, then you take 300 meters divided by 2 seconds, and you say its speed must be 300 divided by 2, which is 150 meters per second. So the speed is still, as any other speed in town, it's meter per second. So this is in a nutshell what waves are. Of course, the whole lab is going to talk about this. Any questions? Okay, so let me share the lab then, if you guys don't have any questions. We have quite a few people who are not here. I'm going to wait a few more minutes before I take the attendance. So waves are everywhere, whether we recognize it or not. So they are prevalent everywhere. And the waves that we're going to be studying today are basically a sample of what we can see. This is basically a representation of a wave. This is a picture of a wave. When you take a picture of a wave, for example, you go to the beach and you look at the oceans next on the beach, on the sea, and you take a picture of them. That is, you took a picture of the wave. So in a sense, then you know how that looks like. So you measure the distance between each basically crest, and then you say this is actually the wavelength of that disturbance of those waves. Okay, so that's basically a picture. So the distance here is in meters. So from here to here, it's 1 meter, and this is 1.5 meters. The amplitude in here, the disturbance in here is whatever units you're looking at. If it is, for example, the water is how many centimeters is up and down above the calm water. So the calm water is calm. The water can go up, rise above the calm water, and come back below the calm water. So that's basically what you're looking at. For example, if the water waves, the surface water waves. If it is, for example, you're talking about sound waves, then you're talking about how much your eardrum is moving back and forth. More precisely is the pressure, the change in the pressure that is caused by the sound. In this case, if it's a pressure, it's going to be in Pascal. Actually, the units for pressure. Yeah, the units for pressure are Pascal. So it's going to be in Pascal. Or the density of the air, because the air. Remember, I told you that it's going to be compressing and decompressing. So basically, that is also another way of looking at the units on the y-axis. So if that's the density of the air being compressed and decompressed, So it's going to be actually in grams per centimeter cubes or kilograms per meter cubes, depending on the unit. That's why the unit in here is depends, okay, whatever you're trying to measure in this case. So this is a general wave, just to get us started on the wave. So what we did in here, we took points A, B, C, D, E, F, G, H, and I. And you're asked questions. The first question, which pairs of letters on the illustration above could be used to calculate the wavelength, and what is the wavelength of this wave? So remember, I could take this crest and call this distance from here to here my wavelength. Or I could take this point B and connect it directly. In other words, the state of my wave, it was going up, up, up. Then I'm not interested. I want to be back in the same state as I am going up right now. Right now I'm going down actually. So this whole thing doesn't count. Now I'm going up, but I need to be in the same level. So going in the same direction and the same level, therefore B and H also could be candidates of measuring the wavelength. I don't have anything counterpart to D here. I don't have another point in here. They did not give me another point. If I start with E, it's not G, because here I'm going down, here I'm going up. So this is not a wavelength. Between F, there is nobody in here, this way or the other. There is another point, A. This is where the wave vanishes. It's equal to 0, and it's going to rise and come back. So this is vanishes again, but this is coming back, not it's going up. So I don't count E as it, and then continue to G. So basically, the answer is A and G, or B and H, or C and I. That's your choices. There is no other choices in here in this example in here. So then you're supposed to measure this distance from here to here, for example, or from here to here, and from here to here, and tell me what that unit is in meters. So you're going to measure it and tell me the wavelength is, and you're going to answer this one. Is this question clear? I need feedback. Do we have any questions? Okay. So the question is asking about the wavelength. The question is asking about the wavelength. And how can we find the wavelength? The wavelength is the distance in the units of distance, which is meters. It's the distance between a crest and a crest, for example, or two equivalent points on the wave. What I mean by equivalent, they have the same amplitude and also in the same direction. For example, B, D, and H, they all have the same amplitude, the intensity, which is 1. So B is unit 1, D is 1, and H is 1. So they have the same level, they have the same height. However, B is going up, D is going down. So that excludes one or the other. But since H is going up, therefore H and B are equivalent points of the wave. Therefore, my choices are either C and I, because they're equivalent. Actually, this is where it peaks in both cases. If I have another where it goes down, I could use that too, but I don't. I have only 2 peaks in here I can see. So C and I, they're equivalent, or 2 same level points in the same direction, namely B and H. Or the points A and G, they're also same points. Why? Because here it vanishes, and you tell me, oh, here also it vanishes, E also vanishes, and G also vanishes. But I tell you, E should not be included because of the fact that here it's going up, the disturbance is going up, here it's going up, so both of them are identical, except now it's going down. So this is not good. Okay? So do you guys understand why A and G are also another candidate? Take a ruler, once you look at this screen, or you count the number of squares in there, and measure this distance from here to here, or from here to here. And each little square in here. From here to here is 1 meter. That means from here to here is half a meter. That means this is a quarter meter. So this is a quarter meter. This is half a meter. This is 1.5 meters. I mean, 3/4 of a meter, I'm sorry. And this is a meter. So then you're going to report your data in here. Is this clearer now, Jasmine and Alexis, and anybody else? That's your call, Brandon. I'm saying it looks to me, but you're probably going to decide it's probably more or less. Jasmine, okay. Okay. Now in here too, we're back into the same question. 2 also is related to the same graph here. What we're asking here, which pair of letters in the illustrator could be used to calculate the wavelength? Oh, sorry, this is A. Which pairs of letters on the illustration, that's question 2, could be used to calculate the amplitude, and what is the amplitude? I want to find the amplitude. The amplitude is the maximum disturbance, how high it can go. So what I can do is take the distance, because this is 0, this is equilibrium, and the height is C or I, or also in the negative direction. So any combination, the distance, the vertical distance, not this oblique distance. Don't take the ruler and measure this distance. What is my tools in here? Let me get the common tools. So it's the vertical, not this distance. This is wrong. So what you got to do in here is, if I can delete it, is measure the distance between A and where C is. That's that distance. Or between E and C, or between G and I, or between F and G, or between F, and it's a distance, so the sign doesn't matter. We're going to come a distance with it in units of meters, okay? Or units, whatever those relative units are. So this distance is a positive number. So the fact that F is in the negative region doesn't matter. You're measuring just the distance, how big that value is. So that's going to be the answer to question 2. So any combination of F, E, G, I mean A, E, G on one side, C and I, and F on the other side. The distance between A and I, which is this same distance, by the way, because we are at the same level. So this is the vertical distance, not any other distance, not this oblique distance. So when I say that, I don't mean that you come in here and say, oh, this is the distance I'm going to find. This is wrong. It has to be the vertical in the y direction. So the last one is not correct. Yes? Is this clear for question number 2? And you're going to tell me what that amplitude is. Okay, very good. So now we're going to use this chart now to represent how the wave has traveled, basically. As I said before, the wave was at some point A, and then it moved from A1 to A2, and from B to B1. So the entire wave has shifted actually to the right now. So this is not 2 waves, it's only 1. But because you're looking at it at a later time, so basically you're looking at it earlier and now where it is. So it's moving to the right, okay? Not all waves, like I said, move to the right. Some of them move to the left. So in this case, it's characterized by the period T, the time it takes to do one oscillation, okay? And also, so those are 2 pictures in 2 different instances, okay? So that's why it looks like we have 2 waves. And the frequency is 1/period. And the wavelength, as I said, is the wavelength is measured, they use lambda for it, and the expression for it is lambda over T, and since 1/T is frequency, so it's also lambda times frequency. in this example in here, they tell you how to do this thing in here. So basically, if lambda is 1.2 meters and the period is 0.4 seconds, the frequency is just 1 over. Just you take the whatever period is and you invert it, and you're going to find the value of f, and as I said, it's expressed in hertz. The speed is v divided by that number, by the period. And you're supposed to do the math, and you're supposed to find 3 meters. So let's click on this link in here that I provided for you. And we're going to do this in here. It pulls up this wave in here. This is what looks like a string. And the first thing I can do is just to look at the wave in here moving. So this is a disturbance, as you can clearly see, moving to the right. I don't know how it is on your screen, but on my screen is moving to the right. And then I'm going to stop it in here. So after several oscillations, stop it. And this wavelength is a short wavelength. I'm sorry, you're not seeing it? Sorry. Is this better now? Sorry. Sometimes I forget myself. And when I do this, it goes away. Okay, so if you're chatting, I can't see the chat. So if I don't see you, that please go on the speaker. So anyway, so when you click on that link, you're here. The one from the PDF file, you come in here. So basically, again, I'm going to have this one go for a few oscillations. This is a wave. And this is basically a wavelength. After several oscillations, I'm going to stop it. Okay. And just to contrast it with a longer wavelength, you see how the wavelength is different. This has a longer wavelength than the first one. The first one is repeating much closer. The distance, again, between peak and peak, between this peak and this peak, is the wavelength. Or between this point and this point is the same distance. If I do a long wavelength, again, the wavelength is this whole distance now. So let's go to oscillation in here, the one that is interest to what's in here. So basically, if I plug in here a different number, this is, for example, my initial example, 300, and did I say the period is 2 seconds? So the frequency is 1 over 2, which is 0.5 hertz, and the speed in here is lambda over t, which is 300, it's 0.015 meter per second, because this one is assuming, what is it? Why is it giving me this number? I think there is something wrong with my formula. Can I fix this quickly here, guys? So T, no, that's not it. Okay, I need to fix this. So I need to fix the expression in here. Oh, it's probably not there at all. So let me go into the properties of this thing in here and try to fix it. Hopefully it's going to work. So we're going to go to text in here. Oh, it's divided by lambda. No wonder. The period and the velocity is not, it's backward. It's lambda divided by period. I'm sorry. Lambda divided by period. I'm glad we caught this one. Otherwise, you would guys have all kinds of wrong numbers in there. So let's try it again with a different thing in here. Let's, for example, put, I don't know, the original one, 1.2. And how much was it? 0.4? 0.4 seconds. Okay. So the math should add up correctly. So let's go back to stop this one. So what this one is telling me 3 meters per second as it should be. So let me stop sharing that screen and go back and share with you guys the PDF file. So it says in here, if lambda is 1.2 meters and the t is 0.4 seconds, the frequency is 2.5 hertz and the speed was 3.0 meter per second. So the calculator now works. I'm glad we did that. Otherwise, we would have gotten some nonsense from everything else. Now you're going to go back to the calculator if you want to. You can do it manually if you choose to use it for lambda that is 3.6 meters and t that is 1.6 meters. So it's the same graph if you like, and you should be able to get the this one working. Is this clear? So far, so good? Okay. So question 3 is good. Question 4, how are the wavelength and period related to the wave speed? Is the amplitude related in any way to the wavelength, period, or frequency? Obviously, the answer to the first part, how are the wavelength and period or frequency, doesn't matter, related to the speed. This is the expression they're talking about. The speed is equal to the ratio of the wavelength with respect to the period, or the wavelength times the period. So that's basically what that is. The last part is the amplitude. The answer is no. The amplitude has nothing to do with the wavelength or the period or the frequency. That has to do with nothing. That's just the intensity of the wave. Okay. So far so good. This is not it though. Now we are going to be looking at, first of all, we talked about transverse waves. Transverse waves are waves that go up and down versus the direction of travel. So you're going to be clicking on a bunch of YouTube. This whole thing is about clicking. This whole lab is about clicking. So in this YouTube animation, it's in this link. So I'm going to click the link. So I'm going to stop sharing and then click it so that it's going to, or let's click it in here because it's going to go very quick in here. So the video is very fast. So I'm going to stop the video first. Okay, and I'm going to stop sharing the screen and go to where it popped up and basically play the animation. The animation is 0.08 seconds. So it's not even a tenth of a second. I mean, 8 seconds, I'm sorry. So it's going to go very quickly. You see here, what you are noticing in here, the whole thing is going up and down and the wave is traveling in this direction. So what you're saying in here is a specific point of interest that was marked in red. Which way this point is it moving? Is it moving in the direction of the wave or is it perpendicular to the wave? As a matter of fact, the whole medium doesn't go anywhere, but the wave is traveling. So the question begs itself is, what is traveling then if the medium basically bobs up and down in its place? And the answer, of course, is the energy. That's all that's moving, but nothing else moves. The material is going up and down. Yes, in doing so, it's carrying energy in one direction or the direction of the travel of the wave. So again, you're going to continue with only a font. What is it? Very short. Okay, so don't be canceled. And go back into the stop and go back into the other one. Share. So you did that. Then the longitudinal waves, again, you're going to click on this link to understand what the longitudinal waves are. The longitudinal wave basically is that, again, the material is going back and forth, but in doing so, the wave is moving. So the material itself is staying in its place, going back and forth. So when somebody speaks and you're next to them, it's not the air that travels to you. It's the compression in the air that travels to you. So the air next to his mouth, it stays next to his mouth. The air next to your ear is next to your ear. But what travels actually is a disturbance itself, the compression and rarefication, compression and rarefication of the air. So I'm going to click on this thing in here. So at the end of the day, again, what travels is the wave. And let me stop it quickly before it gets started. Okay, why did I get the same link? Oh, I clicked the same. Okay, I'm going to stop that one. I'm going to start sharing with you guys the link after you click on it. Share the new link. Again, the disturbance is a sine wave equation, sine wave. but the dots are actually the medium. So I'm going to restart it again in here. So the dots are the medium. Notice the red one. It's going out of its equilibrium back and forth, back and forth, back and forth, but it's not really traveling from end to end, just traveling in its surrounding. So look at the red, look at everything else, but this disturbance is going from end to end. So what is traveling actually is the energy in this case, the disturbance itself. Let me cancel and let me stop the sharing in here. Let me go back to the PDF file and share. So question 5 in here, you may have noticed that one of the dots in these two animations is colored. This is done to make it easy to keep a track of it. Does the red move across the screen? And what does a move with the wave? So you guys understand now. So what it doesn't move across the screen. You can clearly see, and you repeat this a million times, it will not. What travels actually is this thing, the energy, which is expressed in terms of the power. As I said earlier, the power is proportional to the square of the amplitude. So the amplitude matters not for the speed of wave or anything like that, as it matters for the power, which is important, because a loud sound can hurt more than a not loud sound, and that is because it carries with it more power. So the water waves now, there are a lot of animations in here. I really want you to go through each and every one of them. And let me stop at the minute it comes up in here. And restart it from the beginning. Stop sharing that screen and share with you this screen. So now I'm starting the animation in here. Again, look, the water is going in circles. Basically, the droplets of water or the components of the water surface, they're going actually in circles. Okay, they're going up and down, but in the same time going sideways. So they're doing kind of both. Okay, but they're not going from end to end either. So they also fulfill the requirements in terms of what is traveling. It's the wave, the disturbance itself that is traveling. Not so if you go on the surface of the water and basically throw a rock or something on the surface of a pond, you will see that disturbances will travel from point to point, and the water, which creates a splash, will go in and out, and probably goes back and forth, up and down, up and down, up and down, until the motion starts to slow down until it stops. But that disturbance creates circular, basically, oscillations that travel throughout the entire medium. At least the surface of the medium does. You guys understand these ideas now? Now the torsional wave. Basically, it's like the twisting wave. That's what the torsion is. Torsion. Okay. The only thing that can work to see what's going on is, okay, very good. So let me go back into this one in here. So the torsional wave, there are a lot of links in here. I don't know if we should really go through each and every one of them because the explanations are in there. You may have noticed that the main difference between this type of waves is that geometry, which 3 of the above 5 types are simply combination of the 2 remaining. So there are only these 2 fundamental ones, transverse and longitudinal. Anything else is just a combination of one or the other. It's either one or the other or combination of both of them. That's all. Like, for example, the surface waves, the surface water waves, which does both. So they're either one or the other. Okay, they can be either transverse or longitudinal. There is nothing in between. Okay. Seismic waves also express that through the P waves and the S waves. If you guys heard of it, that the earthquakes come in two. The first one is a fast one, and then followed by the second one, which is more damaging, because it has the amplitude that really can cause a lot of damage. So, and they travel with different speeds, though, the seismic waves do. That's why we feel one before the other. So the question then is, go through each and every one of them, and please try to decipher them. You can click on the torsional if you want to. I'm going to click on it just to show you how this one more time in here, how this thing looks like. Okay, I guess I need to go back to see what's going on. That's not the one. Cancel. Where is the torsional? No, that's the water wave I clicked on. Torsional is here. Did they give you the wrong link for it? I think I did. Look, these two links are identical. Please let me know. I will give you the better link to this one. Okay, this is wrong. This needs to be fixed. So this link is not correct. As a matter of fact, let me try to find it if I can find the link. Okay, so here it is, the link for you guys. I'm gonna post it first on the chat session so that you guys have, that's wrong, okay, the one that you, it's the same link. So this is the correct link, okay, for you guys. I'm gonna post it back on the, no, not to you only, to everybody, I'm sorry. To everyone, I sent it only to Ivan. Okay, so this is the correct link, okay, that you guys need to have. So let me start sharing that link now. And it's this one. You see, this is the torsional, the one I was talking about earlier, okay? So there is no compressional wave in here. There is no longitudinal wave. It's all basically twisting, basically, in this case. But you can break it down into two components of the twisting. Both of them are like transverse in this case. So the direction of travel is in this case here, and the disturbance is going up and down in here in respect to that. So let me stop sharing the screen quickly here. Yes, I'm going to post it on the discussion board there for this lab so that you guys fix that. If anytime you find something wrong with the lab, because it was a nightmare getting all of these videos. First of all, it's not just one. I mean, you guys have seen probably so far only a fraction of how many videos in here. There's another one in here. There are one video in here, two videos in here, and actually there's another GeoGebra activity in here. And I'll tell you what these things are in here. So this is for actually for the, this is important, okay? This is not neither. It's not transverse. It's not a longitudinal wave. It's not even a wave per se. Nothing is waving in here. The wave function of quantum mechanics is a probability function that basically used to calculate the position of the momentum or whatever you're trying to, energy or whatever you're trying to use in there. So this is called a wave, and it behaves at least mathematically like a wave, but it is not really a wave in per se. So I'm going to click on one of these YouTube videos or even on this GeoGebra activity that we created for that purpose, and let me stop it once it pops up. Okay. And let me share screen now, which is this one. So this is the wave in here. So the green is the quantum wave, and the actually the calculation for the probability in here. Okay. So that's basically what that animation will show for you. If you go to the GeoGebra activity, you will learn more about these things in here too. What is the? So this is neither. It does not carry energy with it. It has a mathematical concept really. Let me share back the screen in here with you guys. So I think probably, I don't know. This has now phase velocity because The dispersion law that I mentioned earlier is sometimes called this law is called the dispersion law, the one I mentioned earlier. And all of the waves, in this case, they're all basically in phase, so they don't disperse. But in this case, in here, we have something else. Some waves are moving faster than others, and you have their group behavior now is called the group velocity, versus each one of them is probably moving with its own speed. So in here, this is not, you know what? I will think about this question 7, okay, before I probably make a panel on it. Okay. Now, the next, so this is, the first part is just to introduce the two types of waves, transverse and longitudinal, and their properties, really. The first objective is just that's it. Now, this is basically the interaction of waves, or should I say the I'm trying to go through this entire thing, trying to give it some sort of a summary here. Yeah, interaction of waves, okay? How waves interact with themselves and with different media, basically. So that's really what this whole thing is. Okay, so first of all, what is 1? So the types of waves is objective 2, and the first type is basically the properties of waves. So we have 3 objectives in this whole lab. The first one is the properties of waves that we talked about, wavelength, we talked about the velocity, we talked about the amplitude, we talked about everything else. So those are the wave properties. Now the types of waves was the objective of number 2. There are basically 2 types, A and B, okay? And anything else is just a combination of the 2 or neither, like F, okay? So that's basically objective number 2. Objective number 3 now, how do waves interact with one another, basically when 2 waves collide, or with different media? For example, a wave bounces off of the wall, or for example, is transmitted from the wall to another medium or something like that. So that's basically the laws that we're trying to study now. How do waves interact with other waves or with other media? One of them is the law of reflection. And the law of reflection basically states the following. The incident ray, when it hits the mirror, for example, when you're standing in the morning in front of your mirror, and you look in the mirror, you see a reflection of everything that is you. When you look at your toe, you see your toe. Actually, what you're looking at on the other side of the mirror is a reflection of your toe. So there is no toe on the other side, or head, or arm, or anything else. So hopefully that clarifies the issue that probably puzzled you for years. Okay. So anyway, the angle of incidence and the angle of reflection are equal. So that's the law of reflection. And in here, it goes into videos that you do that basically, and it goes even into surface waves. It goes through a lot of details in here. So let me stop sharing that screen and start sharing this screen now. Cancel. Can I replay it? So here is a wave. It hits a medium and it bounces back off of it and basically comes back the way it was. Okay. So this is one kind of reflection, and this reflection, the reflected wave and the incident wave, they're in phase. They have the same phase. Notice in here, when it hits the medium, the disturbance rises up and comes back up. So this end is a free end, basically. So once it hits the medium, at some point, this point in here is very high, and then it's going to reflect back. So in this case, the reflected wave is in phase with the incoming wave. So the one that was traveling to the right and then one traveling to the left, they kept their phase in such a way that the disturbance, if it was up, stayed up, did not really flip on you. Versus the second one, which is, let me go and share with you the PDF first, so that they can see it. So I click the one that is in phase. Let's click the one that is out of phase, and hopefully it's a different one. Let me stop it because it goes so fast. If I don't stop it quickly, I might lose it like before. Okay, so let me stop sharing that screen and share with you this screen now. And here, when it hits the medium, it's not going to travel up. It's going to basically, the medium will force it to change direction and come back in the opposite direction. So the wave was going up, and then the disturbance in here, this point is fixed now. It's like the rope, for example, when you attach to the wall and you start playing with it. The disturbance that is leaving your hand is going up, then when it hits the wall, it comes back on the other side, reflected. And basically, and also inverted. So in this case, the reflected wave is actually going to be inverted. So that's how it's coming back up. Versus if you take, for example, like a ring, and you put it on a post and attach to a string, and you do that for the first one, the ring will rise up and down in the pole, but when it bounces back, it's going to bounce back the way that it came back originally. So that's basically the difference between the two kinds of reflections: the ones that keep the phase and the ones that flip the phase from a positive value to a negative value, or from negative value back to a positive value. So had this disturbance came this way, it's going to be inverted to the top one. So that's basically what the. Let me go into. So this is the. In addition to the reflection, we have which of the two waves can the boundary move? It's going to be the first one. Okay. I'm missing two videos in here, I guess. Okay, there is another thing that I need to do for you guys. This is my notes, okay? So this is, I need to fix this. That's for me. Okay, but then we have more videos in here about the refractions. No, still we're dealing with the reflections. Reflections using different media in here. Some of these videos are actually long. One of them actually is 4 minutes. So you probably, you need to spend a lot of time on this one in here. So this is again, checking the law of reflection and refraction. So let me stop sharing that screen with you guys and sharing this screen with you here, if I can find it. So this is that link. So the angle of incidence, look at he's changing so this is the incident beam in here. Right now it's reflected back. So as he rotates it, look at the angle now. This is the normal to the surface. This is the angle of incidence. This is the angle of reflection. So this is continue now, and the equality is perfect. This is 20 degrees, and the other one also must be 20 degrees, and it is. Okay. So that too is 20 degrees. So the two angles basically are identical. The reflection and the refraction are identical on a flat mirror, of course. That's what we're talking about. At least if we do it on a mirror. Okay. Even on the non-flat mirror, the angle of reflection and angle of refraction are going to be equal point by point. But you take an image, for example, on a concave or convex mirror, and the focusing now is different. But point by point, an incident beam that hits a concave or a concave mirror is going to bounce off of like this one, and in this point, the angle of incidence and angle of reflection are going to be the same. How sharp a point is reproduced depends on the sharpness, basically, of that mirror. So if it's diffused, the image will be out of focus, basically, and you have to either move the object away or closer so that from the focus, so that you get better, more focused image. So this doesn't matter what type of mirror you have. This law works all the time. And basically, we are continuing. All of these videos are, I hope that you guys go through them answer the questions. If you still have any problems, please let me know. Now, in addition to the reflection, there is the refraction. The refraction is basically an incident beam like this one, theta I, is going to be refracted in such a way that, look, it's as if it's coming straight out. But it's going, because this medium has a different index of refraction than this one, like this is air and this is water, for example, then the image appears in a different location than what it should be. Now, something very important when you're doing the laws of waves, how they interact with surfaces, all of these angles are measured with respect to the perpendicular to the surface. So this is the surface, this angle is measured not from the surface itself, but by the perpendicular to it. So this is the angle of incidence, and this is the angle of reflection, and they are measured with respect to this normal. How far are we? If we bring this incidence to 90 degrees, basically from our vantage point, it's actually the angle of incidence 0. And the further you deviate from this, the bigger the angle gets from here. Not from here. It's not 90 degrees if the angle of incidence is just straight out. So in that case, the angle of reflection will be straight out, just like in that demo. In this case, again, the measurements of the refraction are also with respect to the normal. So you draw a normal to the two surfaces. And in this case, you draw the angle for the incidence and the angle for the reflection with respect to normal. Usually, because medium, the angle of refraction in this case is smaller than the angle of incidence. So it's asking you all kinds of questions, and this is the law that governs them. Okay. And if you're asked to do calculations, you should not really worry too much about it, because I think there is an activity where you're supposed to do that in here, okay? It's going to give you all of the things that you need. So in this case, if you watch the video, for example, and let me see how long is this video. This is actually 0.04, so I have to stop it right away. It's going to go very fast, this one. Again, look at the media. The waves are coming here, and they're refracted in here. They're broken, basically. And this is how they appear in there. Okay, and the angle of incidence in this case is equal to the angle of refraction in here. So there are all kinds of videos in here to show this point. So let's show the point in here. And there is a file in your lab. Let me stop sharing quickly this one in here. So it's going to be assumed that the N1 is 1. So this number is 1. And theta 1 is some value, and theta 2 is some value, and you're supposed to calculate NR. And let me get this file for you going, first of all, to show you what it is right now. I'm going to make sure that I have the proper files. I have a million things in here open. Let me go to assignments. What happened in here? Assignments. Cancel this. Lab 10. Okay. So it's let me share with you what it is, first of all, which file we're talking about in here. So it's this file, the worksheet file. It's a PDF file also. This, you don't need to turn it in. Actually, you just need to answer the question. And if you want to turn it in, you're fine. Okay, you can do that too. So let me stop sharing that file, this screen in here, and go to it. So I have N1, which is 1, and I have N beta, which is 43 degrees. I have alpha, which is 47 degrees. Add them up, and they should be 90 degrees. This one is 24 degrees, and this one is 66 degrees. And we want to know what the NR is. Obviously, first of all, we need to know what angles we need to be using. I just stated that basically the angle needs to be with respect to the normal. So here is medium 1, is air, and this medium we don't know what it is. So we want to find its index of refraction, probably thicker, because this angle is 24 degrees and this angle is 43 degrees. So n here, r, must be greater than 1, bigger number than 1. So use the angles with respect to the normal are 43. So sine of 43 here is, this is the sine of all of the angles that are given to you. So it's probably this number in here. And a sine of 24 degrees, then a sine of 24 degrees is probably, what is it? This angle in here, that's its sine. So these two values, 43 and 24. Those are the sines. One of them is 0.6820 and the other one is 0.406. Divide this number by that number and multiply it by one. That should give me the index of refraction of the medium. That should give me NR, the number that I don't know what it is. Is this clear? Yes, Desiree, the answer, hopefully yes. Okay, I'm not 100% sure. I will try, honestly, because I'm having problems with this computer big time. So the question is, when can this go video, the video go on YouTube? Hopefully, I'm working on it. Maybe this weekend it will be up, hopefully before Friday or around Friday or something. Okay. Let's continue with the instructions in here. Lab 10. So we know how to find NR from here. We have N1 in here. We have sine of theta 1, sine of theta 2, and you just do the ratio of the two numbers. You don't need to do anything, just the ratio and end of the story, okay? The diffraction is a different phenomenon, basically, when a wave hits a medium, and depending on how big the medium is versus the wavelength. That's why the wave is basically going to go around that medium. It's going to come around to the other side. If somebody is on one side of the room and the other person is on the other side of the room and one of them speaks, sound waves can go around the building and you can hear them, but you can't see them. They can shine a light and you can see the light if they're around the corner, because wavelengths for light are a lot shorter than the building size usually. But if you find a small opening for light, that also exhibits the same phenomenon. So again, this is another way of the behavior of waves. When a wave of a given wavelength has to go through an opening that is of a comparable size to its wavelength, basically it's going to come out as if it's a new wave now, and it's going to disperse depending on the ratio of the wavelength to the opening. Again, I need you to watch all of these videos, please. The interference, I already gave you an example for constructive and destructive interference. And if you want two more, there are in here more examples, for example, on the interference. Let me stop sharing that screen in here. Actually, that was a GeoGebra activity. Was it this one? Yes, this is the, you have two disturbances. One of them is Y1, and the second one is Y2. And at this point, they have no phase difference whatsoever. And you're going to answer a bunch of questions related to this one. So what you do at some point, you vary this number in increments of 10. So right now it's 0, so you make it 10. And the waves now, the blue and the green, the green and the blue and the red, they start to separate. There is a phase shift now. When one of them peaks, the other one peaks later by 10 degrees, actually. You've just put it in there. And this is their sum. The green one is their sum. So if I add, let's say, for example, by 20 degrees, then now the sum is actually decreasing and the gap starts to widen. When the red one goes to 0, the other one comes to 0 later by 20 degrees. You put the number there yourself. Let's say, for example, put 45 degrees, because you're going to do this one. 45 degrees, there is a 45-degree gap between this one and that one, and the sum starts to reduce further. If I do 90, for example, the sum is less, And the two waves, basically, they have a quarter wavelength. This is max. When this one vanishes, the other one is max. When the other one vanishes, the other one is min. So there is a whole quarter cycle between them, because 90 degrees is a quarter cycle. And whatever values, for example, 120 degrees, 160 degrees. The sum now is very small, 173 degrees. The sum is small, 200 degrees, 200 degrees. The sum starts to grow now, but they flip positions. The one that was ahead becomes behind now. So 220 now, 207, 43, 40, for example, 273.12, for example, whichever numbers you put in there, 299, 300, 320 degrees, 360, let's put 350 and see what's going to happen. Now they're almost back on top of one another, 360 degrees. Now the red one is on top, the blue one is behind. If they put 0 degrees, they should swap places now. Or at least actually the colors are adding up right now. I guess that's what we're looking at. 0 and 360 are the same. 310 and no, not 310. 370 and 10 degrees are identical. In other words, this whole thing repeats itself after 360 degrees. Okay. I'm sorry, I said 360 degrees on top of one another. That's actually the same thing, because this thing is periodic and the periodicity is 360 degrees exactly. In other words, 360 degrees and 0 degrees are identical. Okay, let me take the attendance quickly here. Okay, let me stop that. Somebody was here and left earlier because I know the number was slightly more. Okay, so let's continue with the instructions. So basically, you're answering questions about the interference in here. There is the destructive interference. The question is, when do they cancel, and all of that. So it's all related to that activity for the interference. And this question is, you're gonna hunt for that angle when the two of them cancel, when the green wave go away completely. You're gonna change the value by 10 until you reach a point where there is no more. There is no more wave, okay? This is basically now the interference phenomenon, again, that's from two different sources, source 1 and source 2. You have points in here where there is constructive interference, where the wave fronts hit one another and they amplify, and there are places where they cancel. The wave front, the trough from one, and actually the crest from the other, they meet and they cancel. If they're coming from, actually they are similar waves basically. Otherwise, the intensity drops. Okay. Again, I'm hoping that you guys finish this. There's a lot of videos in here. Dispersion is another thing. Dispersion, for example, when you say send the this is what, like the prism, for example. I tried to do this experiment earlier with my prism. Let me see what happened to it, though. I don't know what happened to it. It was in here somewhere. Bunch of junk in here. Anyway, the point being in here is that you send a beam of light on a prism, for example, which is a not a single color, like white color or white light, for example. It's going to split into different colors in here. So you have the red, the orange, the yellow, the green, the blue, the indigo, and the violet in here. The question was, what does the letter stand for? I guess you know what the answer is now. Okay, so the colors basically split into this things in here, the spectrum. This is the rainbow, basically. This is what you see when you look at the rainbow at after rain. The Doppler effect is something that is related to basically how fast an object is moving and producing sound, or producing a wave in general. So, and this can happen in any kind of wave, whether it's light, whether it's sound, whether it's on the shore, for example, for boats, for example, going super fast on the water surface. So they create this phenomenon. And you've heard that, for example, we're waiting for the train or waiting in front of the emergency vehicle comes by. Before you even look at it, you know it's coming, even if you're driving, because the frequency is set to go higher and higher in pitch, set to go high pitches. And then as it recedes away from you, it's going to be low and low pitches. What's going on in this case is you have the source emitting a wavefront and then moving, chasing it. So for you, the observer, you're listening or watching the wave as if it has shorter wavelength. Since you know that sound has the same speed, it doesn't change. So you say in your mind, in your ear, actually, your brain tells you that this must have a different frequency, because the basic law that we looked at earlier, what is my notes in here? The basic law that basically we looked at it earlier, if I can find it in here, the speed of, let me write it down quickly here. So you're looking at the wave. What happened? Somebody doing something in here, or is it me doing something here? V is equal to lambda over T or lambda F. That's the basic dispersion law. So you know sound travels with 343 meters per second. That's what your brain is telling you, okay? And so in this case, if the wave, because the source sends a wavefront and then moves towards it. When it sends the next one, the distance between them is shortened by how far the source has traveled. So for you, you have a perceived wavelength that is shorter than the actual wavelength. So because lambda appears shorter, the frequency basically appears larger, because V is equal, frequency is equal to V over lambda. So your here tells you, hey, this is a higher pitch. This sound is higher pitch. Now, when it's moving away, when it's moving in the opposite direction, basically it sends a wavefront and moves away from it and sends the second wavefront. So the wavefronts appear to be spaced longer and longer distances between them. So your ear says, okay, I know sound travels with 343 meters per second, for example, for sound or light, it doesn't matter. It's the same speed. But now the distance lambda is longer and longer. So the frequency must be less and less, because you're dividing by a bigger and bigger number. So the frequency now appears to be less and less. So that's basically in a nutshell what the Doppler effect is. The formulas that are involved are a little bit more complicated, but the point is this one, that basically the source creating a disturbance, one after the other, all the time. And as it does, if it's moving toward the observer, it's chasing them. So they appear shorter and shorter, less and less wavelength, so the frequency is higher and higher. Now, if it's moving away from observer 2 now in the same time, so it sends wave fronts and moving away, so the distance between every wave front, basically peak and peak, appears to be longer and longer, which means that the frequency appears to be less and less frequency, higher, a lower tone, basically, frequency. So that's basically what the Doppler effect is. Okay. Now, same thing is happening with the observer too. Let's say, for example, this is the source, and if the observer is moving towards it, it's going to encounter more and more wave fronts at a higher and higher rate, so the sound appears to be higher pitch. If the observer is moving away from it, the wave fronts are still coming with the same lambda distance between them, but with this one and the next one, the observer has moved away, so they appear to be moving. So this can work both ways. The algebra is slightly different, honestly, but the idea is the same. In a nutshell, what the Doppler effect is. It's a very useful thing. I mean, that's how police officers give you tickets, because They send a signal with the radar gun, and based on the reflected wave that comes from your vehicle, they know the change in the frequency, and they can tell how fast you're moving. So they can give you a ticket. Actually, this is not the only place you can use it. Use it also in astronomy a lot to determine how fast objects are moving and moving away from us or towards us and things like that, based on the shift in their color. That's how we do it. So the question here, did you hear about the Doppler effect? Hopefully you can answer honestly. And finally, the resonance. Resonance, for example, a typical example is when you're when there is a child on the swing, although this is not a wave in this case, it's just a disturbance. And if you time your swing so that when the child comes back, you're going to push him again, so the amplitude keeps on increasing until at the end you're going to be have very high amplitudes. Again, this is an oscillation. The example with radio waves also is an oscillation, but oscillations and resonance happen in there, and it happens also. The typical example for resonance in this case is actually sending waves on a string. So if you keep on taking the wave up and down, it hits the medium and it bounces back. Now, if the disturbance is timed so that the next time it comes back, you're going to create your disturbance, a resonance will result in standing waves on a string. Hopefully, we'll try to watch all the movies in here and go through the activities in there and try to understand them, answer the questions. If you still have questions, please do not hesitate to ask me. And the polarization is also another property of some of the waves. For example, electrical waves, electromagnetic waves, for example, light, is characterized by the motion up and down of the electric field and the sideways motion of the magnetic field, as both of them are traveling in a direction perpendicular to that. So both of them are actually transverse waves. So the electric field goes up and down, for example. The magnetic field goes sideways, and then the whole thing is traveling in one direction. The polarization for light, at least, is the direction with which the electric field is moving up and down. Because as the light or the electromagnetic wave hits your antenna, for example, in your phone, the electric field will take the electrons and move them up and down in your antenna, and that signal is picked up by the electronics of your device and later on amplified to tell you that somebody is talking to you. So that's basically, in a nutshell, what is the text going to be cut off on the PDF? What do you mean? I don't understand, Micah. Question 22. Oh, sorry. I need to fix that too. So there is a text in here, fix it. Thank you. That's not for myself, things to do. Okay, so basically polarization, and there are some activities in there with polarizers, basically. That's, you use it to eliminate, because in the case of light, actually, not always polarized so that the electric field stays in place. The electric field can spin, and with it, the magnetic field also. So when you run it through a polarizer, you're going to eliminate anything but the one direction. So in that direction, at the end, the electromagnetic wave that's going to emerges only in one direction. And that's basically the polarization that happens with some of the glasses used for driving, for example, and sunglasses and things like that. So that's basically the idea behind it, is to force only one direction for the electric field, and it makes it easy for yourself, for your eyes, so that it eliminates all the glare, because when the electric field is going all over the place, your eyes are responding everywhere, actually, and the disturbance is not really the way it's supposed to be. Anyway, so you're supposed to answer that. The last question is about the water waves, and water waves cannot be basically polarized, and you should be able to understand that. Why? Basically because of the fact that the disturbance can happen in every single direction, and when it merges back, actually the wavelength in here is going to go around diffuse around the medium that you're trying to use to polarize it if you want to. Okay, this is in a nutshell your lab. It's a long lab. You have to watch all of the videos. I really cannot go through each and every one of them and explain them, but you have to watch them, read the instructions, and if you have any questions, please do ask in the forum. I don't know if I created the discussion session on it or not, but I will if I did not, okay? I will also make sure that you guys have that too. We're good? Everybody? Okay, thank you guys. Can you unblock the discussion board? Yeah, I will. I don't think I did, but I will try. I'll remember not to make sure that everything is working. Okay, thank you guys, and see you a week from today, and be safe, please. Oh, okay. No problem. I'll fix that.